So today we're going to carry on our discussion with electrons in a periodic potential. In lecture number 14, we looked at electrons that were experiencing a periodic potential, but the potential was weak. And we were able to apply the time independent perturbation theory to invoke the concept of gaps between energy levels. So, so the previous lecture was focused on nearly free electrons, and if I were to recount the previous lecture, we came up with the idea of a dispersion relationship, which looks as the following. So I have key k here, and I have the energy here on the vertical axis. I'm going to use this curly e today because I would like to preserve the sans serif e for the electric field. So if we did not have any potential, we just had a free electron gas, and we looked at these free electron gases in our previous module, we'll just have a parabolic dispersion relationship given by h bar square k square over 2m. Now, if we superimpose a periodic potential, which goes as VR equals V R plus capital R, where R is the lattice constant, then in the presence of this periodic potential, this parabolic, this nice, pristine parabolic dispersion relationship is going to be punctuated. And it's going to be punctuated at precise points. So if this is k equals 0, and I'm looking at one dimensions, if I look at the value of this energy at pi over a and minus pi over a, there is a deviation from the parabolic dispersion relationship close to these points. And likewise, so let me draw all the k points which are multiples of pi over a. Here I have 2 pi over a, 3 pi over a, minus pi over a, 2 pi over a, minus 3 pi over a, minus 4 pi over a. And the dispersion relationship is away from these vertical lines that I've drawn, away from these k points, is more or less parabolic like a free electron, but at these precise values of k, it deviates. It deviates in this fashion. So the dispersion relationship is now punctuated, and there are certain gaps between the energy levels. In these green regions, which are forbidden gaps, no energy level exists. And these gaps are proportional to the Fourier coefficient Vg. So this is the dispersion relationship for a nearly free electron. And this is where we finished off our previous discussion, and we were able to find out these gaps with the help of time independent perturbation theory. Okay, and we noticed that these points at pi over a and minus pi over a, they are separated by 2 pi over a. So I can draw a vector going from minus pi over a to 2 pi over a, symmetrically about the zero position of the k space. This vector is nothing but the reciprocal lattice vector, a reciprocal lattice vector. So away from these k points, the electron waves, they are plane waves, they behave like free electrons. But if the value of k for such a plane wave hits a zone boundary, it becomes equal to pi over a or minus pi over a, the energy level, the dispersion relationship changes and it deviates. And this is how the deviation occurs. And the overall result of this deviation is that certain regions, which I've denoted as green in this dispersion relationship, become devoid of electron levels. These are our forbidden gaps. Hence, the picture that is in front of you at the moment is representing the dispersion relationship of a nearly free electron. Now, what is the physical intuition for all of this? Suppose I have a string of atoms fixed in position. They are separated by the lattice spacing A. An electron wave comes in with the momentum k, and it's one dimensional, so this is a plane wave of electron. Its momentum is pointing from the left to the right, as you can see on the screen. Now, if k is far away from pi over a or minus pi over a or 2 pi over a or minus 2 pi over a, so if it's far away from these so-called zone boundaries, and I'm going to explain these zones later, but if it's going to be far away from these critical points, the wave is going to pass straight through. It's not, no scattering will take place. However, if the k hits a certain value, and let's see what that value is, reflection might occur. And we can use the Bragg's law to look at this reflection. So the Bragg's law states that 2 pi over lambda sine theta is, looking at the lowest order, if this condition is met, scattering occurs or reflection occurs. This is the Bragg's formulation of scattering, X-ray scattering. But it also applies to waves of any kinds, be they electron waves. Now, in this one-dimensional example, the sine theta is simply equal to 1. Okay, so we don't take into account the sine theta, and we have a condition. So sine theta equals 1, because you can imagine that this is the plane of atoms, the vertical plane of atoms. The wave is coming in, theta is equal to 90 degrees. So it's a one-dimensional grating in a sense. So this equals 1, and 2 pi sine theta. Excuse me, I'm just trying to figure out a few things. So this is not lambda, sorry. So 2d sine theta. So I need to have 2d sine theta. D here is Bragg's law. So let me write down Bragg's law again. So Bragg's law is 2d sine theta equals lambda. Now d in this case is the spacing between these planes, and the spacing between these planes is a. So 2a sine theta, this equals 1, equals lambda. This is the condition for reflection for electron waves. Now I can replace lambda by k. So because I know that 2 pi over lambda equals k, so lambda equals 2 pi over k. So this means 2a equals 2 pi over k, which means that k equals pi over a. So at this particular value of k, these electrons are going to be reflected. So in this one-dimensional or monoatomic lattice, waves come in. These are electron waves. And if k is of the precise value pi over lambda, pi over a, or minus pi over a, or 2 pi over a, or minus 2 pi over a, then this wave is going to be reflected. And standing waves will be produced inside this one-dimensional crystal. And we looked at those standing waves in our previous lecture. All right. So at these zone boundaries, these standing waves are a superposition of left moving waves and right moving waves. And we discussed in our previous lecture that at these precise zone boundaries, the wave function looks like a superposition of a k propagating wave and a minus k propagating wave with two kinds of energies. One is the energy that is given over here, and the other is the energy given over here. One has a higher energy than the other. So, and there's an energy gap between these two energy eigenmodes. So this is the concept of a nearly free electron that we discussed in our previous lecture. So any questions about this before we move on? So I'm happy to answer any question. So my goal is to give you an intuitive picture of what's happening inside a solid. How do these electron waves scatter inside a solid? What is the physical significance and meaning and interpretation of these forbidden gaps that appear? And I'm going to connect this with bands today. So what are bands here and what is the band theory? So any questions? So the summary is that if I have a zero potential, I neglect the presence of ionic cores. The electron behaves like a free electron. It has a parabolic dispersion relationship. The presence of a periodic potential punctuates this nice parabolic dispersion relationship and creates these gaps. We can find out the size of these gaps by looking at the Fourier coefficients of the expansion of the periodic potential function, VGs. Each gap is equal to 2 VGs. All right. So gaps appear at the boundaries of zones, and these boundaries of zones are at multiples of plus minus pi over a. Okay. So this first zone from minus pi over a is called the first Brillouin zone. And so on, we have the second and the third and the fourth Brillouin zones, and we're going to talk more about them. All right. So, and we can find out these gaps using degenerate perturbation theory. If the electron has a k value which is far away from these zone boundaries, far away from the precise critical k points, nothing happens to the electron. It behaves in a regal fashion like a free electron. Nothing happens to it. Okay, it's only at these points which are separated out by multiples of the reciprocal lattice vector g that scattering can take place. Okay, so when scattering takes place, in this case, the initial k vector is reflected back and it produces a minus k wave vector. Okay, and the difference between k and minus k is equal to g, which is 2 pi over lambda. 2 is equal to g, which is 2 pi over a. All right, 2 pi over a. So any questions before we start on our lecture? So in lecture number 15, we're going to talk about the concept of the effective mass, and we're also going to introduce bands and what do we mean by bands. Okay, and in passing, we're also going to talk about the Bloch's theorem, which is a key fundamental insightful concept in modern condensed matter physics. The whole concept of condensed matter physics, be it low dimensional systems or three-dimensional systems, they hinge upon the concept of bands. All semiconductor theory derives from the concept of bands. Magnetism derives from the concepts of bands. Superconductivity, all of these exotic emergent phenomenon have their grounding in band theory. So we really need to understand and get a physical sense of what bands are and how they are formed. And we already have an inkling to this. When we are discussing this nearly free electron theory, we've actually introduced bands, even though I haven't stated it clearly in so many words. Okay. So before I talk more about bands, and probably this lecture won't finish today, and I also have to do a makeup lecture. I'll do that soon. I would like to talk a little bit about the concept of effective mass. An effective mass is related to bands. So what is effective mass? We know that in most of physics, there is this concept of mass, which is simply how much an object will accelerate in response to a force. Okay, so electrons that are inside these periodically periodically disposed crystalline matter, they also behave like waves and they also behave like particles. They are truly a quantum field. So these electron waves have an associated mass, and we need to understand what is meant by this mass. So mass will always have dimensions of the dimensions of force divided by the dimensions of acceleration. So let's talk a little bit about mass. Uh, so if I have a plane wave, kx, this object in time might be moving with a certain velocity. And that velocity is really called the phase velocity, which is omega over k. This is something that you learn in your basic waves mechanics or modern physics courses. However, it is also possible that waves of different kinds and different k values, they all combine together and they form what is called a wave packet. A wave packet of this kind. Okay. This phase velocity Vp can, by the way, be uh, higher than the speed of light, but it is really the wave packet. When an electron is moving inside a solid, the electron wave function, these waves are simply wave functions, quantum mechanical wave functions. So when an electron is moving in a solid, it is really not a plane wave, because a plane wave has no beginning and no end. It just goes from eternity to eternity. It spans out the entire space. But an electron really is a localized particle in a sense. So there's a certain probability distribution function of the electron, and that can't go out anywhere. There's not a uniform probability distribution. Rather, we talk about wave packets. The electron could be somewhere here if you just want to draw the cartoonic picture of an electron. And this wave packet is being piloted by the particle that we call an electron. Now, when you have wave packets of this kind, it is composed of many different kinds of wave functions. Okay. So if you would like to write down the wave function for this electron at some time t naught, this would be equal to the Fourier transform of the wave function, and then you would like to sum up over all the values of k, and then you have tk here. Sum up over all the values of k's and you'll get the wave function. So each wave function is being modulated. This is the plane wave, and each one of them is being modulated by a Fourier coefficient. And if you choose and fine tune your Fourier coefficients, you can construct this wave packet. Now, if you look at the wave packet could also be moving with some speed. That speed is called the group velocity. Okay, and we define the group velocity by d omega over dk. So what I'm going to do, I'm going to refer you to one of my lectures from the modern physics class, which talks in detail about the distinction between the phase velocity and the group velocity. But this group velocity is the velocity at which the information is traveling, and the information here is the electron density of the is the electron density. Okay, so we define a speed. So this is emblematic, or this is representative of the speed of the electron. So if I take the derivative of this speed, I will get something that is proportional to the acceleration. Okay. Now, I also know that the energy of a particle is given by h bar omega. So if I were to find out d omega over dk is Vg, I can write this as 1 over h bar d E over dk. So let me write this E in this curly fashion. Okay. So my Vg is 1 over h bar dE over dk. This dE over dk is the slope of the dispersion relationship. Okay. Now, if I would like to find out, if I take the derivative of this velocity, I'll get something proportional to the acceleration. So let's look at the acceleration. dVg over dt is 1 over h bar d square dE dk dt. And I can also write this by the chain rule as 1 over h bar d square e dA square dk over dt. This is something proportional to the acceleration. All right. So now I need to look at this term here, dk over dt. Now we know that the momentum is given by h bar k. Okay. So if I were to take the derivative of this momentum dp over dt, I would get h bar dk by dt. So this dk by dt somehow represents a force. Okay. So now let's look at the force that is acting on an electron. An electron is a charged particle. A force can act on an electron when it experiences some kind of electric field. Okay, so there can exist an electron, an electric field inside a solid. Remember, there is a potential landscape. The derivative of that potential landscape gives you the electric field, because the potential is a conservative force. Anyway, so now what we would like to do, we would like to find out in some sense uh, the following. So if an electron sees an electric field E, now this capital E is an electric field. I multiply this with the charge on an electron. This gives me the force on the electron. If I look at the work energy theorem, whenever a force acts on an electron and it acts through a distance, some distance, which I would say Vg delta t, delta t the time. If this force acts for a distance small time delta t, and the group velocity at that time is Vg, then all of this is going to give me the change in energy in time delta t. Okay, so far so good. Now the change in energy I can always write as dE over dk into dk. Okay, so what this means is, this is from the chain rule. So what this means is that I could write dk over dt as minus e vg my so this is d, so I take this to the other side here, and then this becomes vg, and then I would also need dE by dk here. Okay, now from, let's look at an earlier equation. I know that vg is given here, 1 over h bar dE by dk. So I just replace this vg by 1 over h bar dE by dk minus E. This is dk by dt, dE by dt. I can ignore this. I can just cancel this out from both sides. And this term here is nothing but Newton's law. So we're treating electrons like classical billiard balls. The change in the momentum, h bar k is the momentum of an electron, is equal to minus E. So now I have this expression for dk by dt. I can put it in here. Okay. So let's put it into equation number 3. All right. So if I were to do that, so let's look at equation number 3. dvg, excuse me, dvg over dt equals 1 over h bar d square e over d square dk over dt is minus. All right. So what does this mean? This is a force. This is an acceleration. So this must be the reciprocal of a mass. This mass is called the effective mass. So I can define an effective mass 1 over m star. M star represents an effective mass. And this effective mass equals 1 over h bar square d square. And this, what is this object here? This object here is the dispersion relationship, the slope of the dispersion relationship computed twice. Okay, and I'm going to see what this means graphically. So now we have the concept of an effective mass. We're going to see what it means really. What physical interpretation do we assign to this effective mass? But there's an effective mass for the electrons inside a periodic potential. That effective mass is given by some property of the dispersion relationship. Okay. In fact, the reciprocal of the mass is proportional to the curvature of the bands. This object here is called the curvature of the dispersion relationship. The double derivative is called the curving of the curving. Okay, so that's called curvature. so so now what does all of this mean? This means that if I had an electron inside a periodic potential, if we were to apply an electric field to it, it will accelerate in accordance with this this effective mass. And acceleration causes change in the momentum or change in the wave vector of the electron. So the change in the wave vector of the electron would depend upon this effective mass. Okay. Now I'm going to give an thought experiment that helps you understand this effective mass. But are there any questions about this derivation? Sometimes I need to look at your faces. Unfortunately, this cyber medium doesn't fully allow me to do that with ease. But how is it going? Any questions about this derivation? All right, so now let's look at this problem from a graphical perspective first. And then I'm going to give you a small Gedanken experiment, a thought experiment that helps you understand this concept of effective mass even better. By the way, Jumla Motreza as an A side, if you had just free electrons, for free electrons, we know that the, excuse me, the dispersion relationship is given by h bar square k square over 2m. So let's look at the equation that we've written above. Let's find the curvature. So let's first find the first derivative. This is going to be h bar square k over m. Excuse me. Excuse me. H bar square k square over 2m. So excuse me, something strange going on with my. So dE by dk is h bar square k over m. Take the derivative again. H bar square over m, which means that 1 over m star for a free electron equals m, which means that the effective mass for a free electron, which doesn't see any periodic potential, just sees a uniform constant bathing of potential, for such an electron, the effective mass is the same as the real mass of the electron. There's no difference whatsoever. It is the periodic potential that makes the effective mass go different uh, from the real mass of an electron, which is 1.67 into 10 to the power minus 20, something of this kind, 9 into 10 to the power minus 31 kilogram, I think. Okay, so the effective mass for an electron that is inside a periodic potential is rather be different from the real mass of an electron. And in order to see that, let me look at a graphical picture. First of all, let's draw the dispersion relationship for a nearly free electron. Okay, now I'm going to try to draw some nice figures here. Here you go. Okay, this is my pi over A, right? So this is the zone boundary. Now, if I were to look at the dispersion relationship, this would go like this. It curves down here near the zone boundary and then starts from a gap. Okay, so there's a gap here. This is a gap. Okay, this is my E. Now I take the first derivative dE by dk. I plot it graphically. So here there's a parabolic relationship. So the slope will go up as a straight line. Here the slope is 0. So the slope has to come down. And then the slope goes, then the slope changes again. So here it comes back to its original. And so it's this curve is curving upwards. So this is what the derivative of the dispersion relationship looks like. And there's a notch or some kind of edge at the zone boundary. Now this gap here, let's call this gap Eg, band gap. Let's call it the band gap, even though you still don't know what is meant by bands, but let's call it a band gap. At the band gap, the dispersion relationship, the slope of the dispersion relationship shows a notch. Okay, then if I were to take the slope of this slope again, let's see what I would get. Here the slope is a constant and it's positive. Here the slope is again constant and it's positive. But what do we have in between? In this region, the slope is decreasing. From positive, it's going down. And it can even become negative. All right. And it then starts off, there's a discontinuity here in this curve, in the derivative of this dE by dt curve. And this is what it looks like if you were to take the derivative again. So there is a discontinuity in the slope of the dispersion relationship graph. Okay. And we know that this mass m star is inversely proportional to d square E over dk square. And you observe two things. If this object were negative, the effective mass could also become negative. All right. The effective mass the effective mass can be totally different from the real mass, and the effective mass keeps on changing with the wave vector of the electron. So depending upon the wave vector of the electron, the effective mass is going to be different. And that effective mass is going to accelerate the electrons differently in response to electric fields. Okay. And I'm going to talk about a thought experiment later, but this is how we look at the band, the dispersion relationship, take the derivative of that dispersion relationship, and take the derivative again. All right. Now, this example that I've drawn here is one example. Let me look at another example in which the band gap is much larger. Okay. So this distance here from the zero of the energy to the top of this band can be called uh, it can be called the band width or the width of the band. Okay. Now The example that I've drawn is large widths of band. The band has a large width and a small gap. We can have another scenario, which is true for many semiconductors, which is the following. Let me rub this out for a minute. We could also have another scenario, which I'm going to draw now. That scenario is the following. I have a small width of a band and a large gap. That's also possible. A large gap, EG is large, and the width of the band is small. So narrow bands. These narrow bands, as you can imagine, are formed when from transition metal atoms or rare earths in which the outer electrons are not belonging to they rather belong to the d and the f electrons, which are closer to the nucleus, so they do not extend further out from the away from the nucleus, and therefore the bands remain tight. The band gaps remain, however, large. So this is true for certain kinds of transition metals, rare earths, and many semiconductors. Now, in this case, if I were to take the slope, the slope is still going to be linearly positive, but now the notch is going to be smaller. Okay, and if I were to take the derivative of this again, this is what the derivative is going to look like. The derivative of the derivative, small value here, small value here, and really small interruption here. The discontinuity is rather small. Now, if and this could become negative, this could become negative. Here, there's a higher probability of becoming negative. And now, if I were to take the inverse of this graph, I will get a very large reciprocal. So this is my d square E by dk square. I will get a very large effective mass here because these are small quantities. So the effective mass can be twice the mass of an electron. It could be 1.5 times the mass of an electron. So these are heavy electrons in a sense. So the heaviness or the lightness of an electron wave or an electron depends upon how the bands and the dispersion relationship change. The band structure determines the effective mass of an electron. Any questions?
सर जो आपने बताया था कि mass of electron जो है वो negative भी हो सकता है, तो वो इसलिए क्योंकि हमारी डी स्क्वायर ई ओवर डी के स्क्वायर की वैल्यू नेगेटिव है, और
जी
हाउ
बिल्कुल।
इज इट फिजिकली कि हमारा जो ओवरऑल मास है ऑफ द एंटायर ऑब्जेक्ट वो कम हो जाता है, या इसकी कोई इंट्यूटिव
ठीक
अंडरस्टैंडिंग
है,
अगर दे सकें.
चलें, I'll try. So what is mass? Mass determines acceleration in response to a force. Okay. Now, if the acceleration is negative, the mass will be negative. So let me see how that works. So suppose I have a really, really thin foil of metal, thin foil, and let me draw the dispersion relationship by the side of this nearly free electron K. This is my zone boundary, almost parabolic up to the zone boundary. Then it takes a turn, and then it is punctuated and starts off by a certain gap. Okay. Now suppose an electron wave comes in. I have a beam of electrons firing into the thin foil of atoms. And most of these electrons go straight through. Okay. So I'm somewhere on this curve of the dispersion. I'm somewhere here. Okay. Somewhere here. This is my K value of the incoming electron, right? Now, how do I increase K? In order to increase K, I need to increase the momentum of the electrons. How do I increase the momentum? I increase the momentum by applying a force. How do I apply a force to an electron? I apply an electric field. So apply an electric field, capital E, in this direction, which is going to accelerate the electrons. Their momentum is going to go up. And when their momentum is going to go up, these electrons are going to move up this curve. So this is my dispersion relationship. These electrons are going to move up this curve. At a particular value of k, okay, so you've applied a force, there's a certain time, that force is acting for a certain time, the energy is going to go up, the k value is going to go up. At a certain point, the k reaches the critical point of being equal to or very close to pi over a. And when that is going to happen, so the electron is being constantly accelerated, so there's a mass associated with the electron. At this particular value of pi over a, the electron will have achieved a wave number or a wavelength, so that this electron is going to be scattered off, is going to be reflected because of the Bragg's condition, as we've already noticed. And when it's going to be reflected, the acceleration of this electron has of this electron wave has become negative, which means that the effective mass of the electrons has now become negative. Okay, so this is a physical intuitive picture, a thought experiment that helps us be convinced that this electron can have a negative effective mass. So the effective mass is telling us really the direction of scattering of k waves. In what, how does k change for an electron wave inside a solid? If the electron wave is totally reflected back, then the mass for such a system, for such an electron, has to be negative. Now if you put that solid on a weighing balance, of course the mass is not going to change. But this is the concept of this derives from the concept of bands. The bands have a certain curvature, and that curvature determines the effective mass of electrons. I hope I'm able to get some physical sense into this picture. जी हैदर आपने सवाल पूछा था.
से मैंने पूछा था और समझ आ गई है, थैंक यू।
ठीक है बिलाल. और कोई बात? Now I will probably finish off this lecture here today, because in order to discuss the Bloch theorem, I need a full an hour and a half. This has taken me slightly longer, but let me just introduce the Bloch theorem, and we'll talk more about this in detail in the next lecture, which is going to be next week, by the way. So the Bloch theorem comes in different varieties, and we're going to talk about all of those varieties. The electron, the electrons that we're dealing with so far, they are independent electrons. They're nearly free electrons, not totally free, but almost. They've escaped a little bit from the confines of the atoms, but they're nearly free. They're mostly free, but they slightly deviate near the zone boundaries. Okay, they must obey the Schrodinger equation for electrons, and there's a periodic potential now. So if I write the Schrodinger equation, minus h bar square 2m d square psi dx square in one dimensions plus dx psi x, this must equal e psi x. So these electron wave functions must obey this relationship. Now the Bloch theorem states that whenever you have a periodic potential, the eigenstates can be written, if it were, if the periodic potential was just a constant, then we had the eigenstate is just a plane wave. But if you now have a periodic potential which is given defined by this relationship, Vx plus a is Vx, or Vx plus Na is Vx, where a is the lattice spacing, then this wave function is the original plane wave now multiplied by another function which is periodic in x. So this ux is such that ux plus Na equals ux. So the wave function for an electron inside a periodic potential is really equal to a modulated plane wave. and the plane wave is modulated by a function or multiplied by a function which has the periodicity of the lattice. Now, this looks like something very obvious, but this has deep implications. And this will help us introduce bands. This will help us get a better physical picture of the concept of the reciprocal lattice. This will introduce us to Brillouin zones. Many people pronounce this in different ways. So, Brillouin zones, whatever suits your palate, or the Pakistani way of interlocution, you can pronounce this. But we can get introduced to first, second, third Brillouin zones. And whenever we deal with low dimensional systems like graphene and its various analogs, silicene, tinine, germanium, black phosphorus, phosphorine, and the huge plethora of two-dimensional materials that have come up in modern condensed matter physics, these concepts are the linchpin of it. These concepts are really vital. So we're going to talk about the Bloch theorem and its various manifestations in the previous lecture. So I'd like to end today's lecture at this point in time. A few announcements about the upcoming midterm. The midterm is going to be on Thursday. I've already circulated the solutions to all the 5 homeworks. They will also be uploaded. I will give you about 24 hours to hand in the midterm exam. It's going something that can be completed in 2 to 3 hours in a stretch. It's going to be closed book, closed notes. We're going to follow the honor code. I might follow up your midterm exams with an oral examination, as I've already announced. And I'll give you 24 hours to hand in the homework, the midterm solution by email, copied to Tawqir Zahid. So this is a logistic announcement about the midterm on Thursday. So I wish you best of luck for that. So let me stop recording and then we can talk later.